Okay. Hello, Ionis.
Hello, good morning.
Good morning. I think now we have different speakers, so we can start our meeting and our public workshop. So, hello everyone. Thank you for attending this public VPP4IBOX workshop, and thank you for also for speakers for their great contribution. So the meeting will be public, and I will start the recording also. So my name is I'm Abib Nasser from Mardiap, and we are leading in the communication dissemination in VPP for Ireland. So today we will start by introducing VPP for Ireland. Then David from Schneider will present the VPP4IBOX solution as a whole. And then we have from Cardiff University, we have Sami and Mehmet that will introduce the concept of virtual energy storage system. And at the end, we have Ioannis from present their solution, decentralized energy management platform. Then at the end, if you have any question, feel free to share it in the chat, or you can raise your hand to ask speakers after their different presentation. So I hope that you are seeing my screen. So thank you. So few words about VPP for Ireland. It is a H2020 project, and it is composed of 19 partners from 8 European projects. The VPP for Ireland is led by Marseille University, and it will end the next year. So our project VPP4IBOX aim to develop flexible and innovative virtual power plant VPP, mainly dedicated for European island by using digitalization like digital twin, virtual energy storage system concept, and blockchain. The digitalization will enable the possibility to aggregate different and small distributed energy assets together, like PV, wind turbine, and even storage systems, flexible loads, and any other source of energy that can act together in order to, as one virtual power plant, to store or to release energy when it is needed by the grid or by consumers. And for example, in case of self-consumption, also to provide flexibility and stability for the grid. Our VPP foreign solution will are under integration and demonstration in 2 leading islands, in Formentera in Spain and in Gogşada in Turkey. And then based on the different feedback and lesson learned from the leading island, we'll try to define and generate a replication plan for 3 follower islands to be initiated at the end of the project in Italy, Denmark, and in UK. So our project is facing global challenges like interoperability, difficulty also difficulty to implement and integrate the energy and digital transition in parallel. Also, we have challenges about regulations and the long-term engagement of consumers. Also, there are other specific challenges linked to island to be addressed, such as the higher cost of integration and installation of new solutions, and difficulty to convince actors to adopt energy and digital transition. So, and also we have identified the higher variability of consumption and the dependency to fossil energy, such as the using of digital diesel generator, despite the presence of strong green potential in Ireland. So in our project, we believe that VPP or virtual power plant is the suitable or the appropriate solution for island because it enables the large integration and the various energy source in island such as solar, wind, waves, and hydropower in a decentralized and distributed. So also don't forget that in island there are many islands that are not connected to the mainland, and VPP can offer them a large flexibility and strong flexibility. For example, in during peak tourist season. So maybe our solution, as you can see on the screen, is composed of in 3 layers. So the first layer is the VPP box, the main objective of our workshop today, that will monitor and control the different physical component and assets thanks to the RTU provided by Schneider Electric and the Raspberry and the VSS integrated in the Raspberry by Cardiff University. And so also we have, we can say, edge computing layer provided through the VPP4 node that will allow and will enable to operate the VPP and to enable the aggregation of different assets by providing AI services like prediction, optimization, and other modules. At the higher level, we have the VPP4 platform that will allow to create a shadow, the VPP shadow, the VPP node copy that will allow to simulate in parallel by using the digital twin in order to detect for improvement and maybe to detect deviation and to exchange and federate data between the different VPP nodes. Regarding security, our solution is we are using SAP for authorization authentication, for secured authentication and authorization. So feel free to contact us if you have, even after our workshop, any further question, and you can find more details about our project in different media. So now I think we can go to the next presentation by David from Schneider University, from Schneider Electric. So the floor is yours, David. Go ahead. You can share a screen.
Yes, hello.
Stop sharing. Go ahead.
Not sure if I can present. I think I need to maybe make a presenter.
Okay. You can share it. I don't know if you can maybe send it by email because the organizer was Howland. Is not.
No, can you just make me a presenter? You just right click on my name.
Okay. Let me check. Okay.
Now I can.
I think now you can do it.
Yes, yes. Now I can. Thank you, Javier. So thank you all. Normally you will be able to see my screen now. So this is David Pampera from Schneider Electric, and I'm going to prepare to present an introduction on VPP4IBOX concept. Okay, so VPP4IBOX is a cabinet with processing capabilities to be used alongside with the rest of the VPP4 Islands ecosystem. The main objectives are to gather and to operate distributed energy resources, with several communications interfaces by using IP or serial communications, besides digital inputs, outputs, and so on. So giving flexibility to connect to different assets. Also to be the link, communication link with the VPP4I nodes in order to provide the right information from the field, so different algorithms running on the node can use it and take, let's say, advise actions. Okay. The next one is to run virtual energy storage system algorithms in order to estimate different flexibility capacities, and also some other algorithms with respect to smart contracts, okay, to implement a peer-to-peer trading engine. As introduced by Habib in the introductory slides, there are two demonstrators in the project in which we will be deploying the VPP4IBOXes. So the first one that I'm presenting is about Gökçeada demonstrator in Turkey. And the particularities of this demonstrator is that we are using these boxes in an environment for the distribution system operator in the island of Gökçeada, which is Wedash. And we are integrating wind power plants and solar PV panels. Also, there is the opportunity to integrate flexible loads, diesel generator, and a battery energy storage system in one single location. So it's also a matter of defining many different assets available in one place that we need to manage and control. Also, there was the need to have energy analyzers to measure different electric parameters to be taken care in the calculations. This location, this island, is also providing virtual energy storage systems that we will explain before we continue later on. And then we will have, as mentioned, digital inputs and outputs to operate the flexible loads and remote communications that are required to be supported by the box because it's an isolated area in which sometimes there are no let's say, physical communications available. So we prefer to have a backup system with a remote communication just in case the coverage was not really good. So I'm just here showcasing the architecture that we have designed for this demonstrator in Turkey. There are two types of boxes. The first box, the type on the right, type 1, you see that it's aimed to manage the different assets that I mentioned before, the diesel generator, the flexible load, and a battery energy storage system. We have a remote terminal unit, which are the main elements with processing capabilities and with the option of operating the digital inputs and outputs of the flexible load and diesel generator, and then also able to communicate with the battery energy storage system thanks to several communication protocols. We have also in the box several Raspberry Pis in charge of implementing the virtual energy storage systems. Okay, and then these 4G or wired communications, both options are possible to communicate with the node. On the left-hand side of the picture, we can see several VPP4IBOXes Type 2, which have a simpler design with just the remote terminal unit, and then the energy analyzer and some communication modem. Okay, and in this case, we are just having a direct connection with solar and wind farms. Okay, in order to get the data, but without implementing these VSS services, as in Type 1 boxes. At the beginning of the project, just for your information, we were thinking in having one single box per type of asset, but it was more cost effective to combine several assets into one single box, as in Type 1, in order to have a more optimized structure of boxes to provide these services. Now we continue with the needs for the demonstrator in Spain, which is in the Formentera island. So in this case, we don't have the distribution system operator on the island participating in the project. So we are using the VPP4IBOXes in relevant buildings owned by the local government in the island. In this case, we are integrating also PV panels and the energy analyzer. We are having them to measure different electric parameters. And as an advanced service, we are having the smart contracts one to provide some services to energy communities. Again, we are including also remote communications, just in case there are some IT issues that make difficult to communicate with the boxes. So this is the architecture, similar than the one that I presented for Goxeada Island. In fact, the design of the Type 2 boxes here is the same than in Goxeada, but Type 1 boxes here in Formentera are slightly different, as we are just having one single asset being monitored. Okay, in this case, we are having the solar panel, and in this other one, we will have some fuel cell and electrolyzer. And with respect to the smart contract services, we are having one Raspberry Pi on each, running these services and communicating with the applications in the node. Just some 3D renders of the design that we prepared based on all the requirements that we received for each of the islands. So we have this, let's say, larger box for Goxeada, Type 1 box, with the remote terminal units, the Raspberry Pis, and the communication elements. And on the right side, we have the Formentera Island box, which is a smaller one with just one Raspberry Pi and one RTU without acquisition modules, as mentioned. Then we continue with Type 2 renders, which are the other more simple boxes. In this case, just the RTU mainly and the energy analyzer without any kind of Raspberry Pi. And here just some real-life pictures of the actual boxes in the demonstration sites. So just one example of them. So the one on the left is for Goxeada, and on the right, the one that we are using for Formentera. So currently, as mentioned, we have like 4 boxes in Goxeada and 5 in Formentera that are deployed in order to leverage the services that are provided by other partners. That's it from my side. So now I give the floor to Saif or Mehmet in order to present about the virtual energy storage systems.
Thank you, David, for your presentation. So, Sami or Mehmet, if you can, yes, you are a presenter, you can share your screen.
Yeah, I've just many thanks, Habib. Many thanks, David. Can you see my slide? Brilliant.
Yes.
Yeah, thanks.
Yes, okay, go ahead.
So in this presentation, we focus on the solution that we developed, we manufactured by David, as he's explained in a minute. But a quick introduction to a VSS. So a virtual energy storage system, or in short, VSS, is essentially a combination of different controllable, distributed, renewable energy resources and non-renewables as well. The combination aims to function similarly to a large conventional energy storage system. In terms of application, since the VSS essentially is forming a synthetic energy storage system at distribution and transmission levels, it can provide services at both levels. Essentially, those services or applications of a VSS can be categorized into 4 groups. The transmission and distribution systems are essentially sized to accommodate the expected peak demand. Reducing the peak demand through the VSS allows the system reinforcements to be deferred. Also, VSS can reduce the required spinning reserve capacity and increase the generation loading level, because the availability of the VSS capacity can continuously reported to the system operator, and at a fast can act as a fast spinning reserve. The VSS can also provide different ancillary services, such as frequency response service. A VSS also can smooth the variation in the power output from the intermittent renewable generation, and that leads to increase in the hosting capacity of DGs in distribution networks. So this is a general overview of the concept of the virtual energy storage system. The solution that we've developed with the help of our partners is an energy management, power management algorithm. This management algorithm is called VSS Engine. As Habib mentioned, the solution developed in this project has 3 levels. So the platform, the node, and the box level. Our solution, the VSS Engine, will be deployed, as David mentioned, at the VPP4IBOX level type 1. A VSS in this project is a combination of a flexible demand, a battery, and a diesel generator. The flexible demand and battery will be installed by the project. 6 kilowatt of flexible demand, 50 kilowatt, 100 kilowatt hour battery energy storage system. In addition to the diesel generator exists on Gotchada Island with a maximum capacity of 590 kilowatt. So in normal conditions or under normal circumstances, an optimization engine, an optimization algorithm deployed at the VPP4I node controls those VSS components. So essentially schedule their operation or sending their operation setting points for the next hour at 15 minutes time steps. But when the forecasting error is calculated by an algorithm deployed at the VPP4I node level, it's called forecasting error quantifier. Essentially, it's compare the forecasting of renewable generation with the real generation output from the island. We have both solar and wind generation. So when that forecasting error exceeds a certain value, which we've set to 10% of the forecasting value, this simple algorithm, which is called forecasting error quantifier, will activate the VSS engine. When the VSS engine is activated, it's essentially performs 2 functions. So it's a quantify and report the available power and energy from the VSS. More importantly, it's coordinate the operation of the flexible load battery and diesel generator in order to mitigate the error in the forecasting of renewable generation. So the VSS engine follows simple rules. It sets two different priorities for charging and discharging of the VSS. That's mainly to reflect the aim of minimizing the operation, the fuel consumption of a diesel generator, and the operation cycling of the battery. So in the charging mode, where we assume to have a positive forecasting error, which means that there is a surplus renewable generation. The VSS operating in a charging mode, so to start by reducing the generation from DG, then consumption increase in flexible load, and if that wasn't enough, then the battery energy storage system will be charged. On the other hand, in this charging mode, a flexible load is prioritized, then battery, then diesel generator. I will invite my my co-worker and researcher, Dr. Mehmed, to present more about communication. Mehmed, the floor is yours.
I think I was muted. Sorry. Thank you very much. I will share my screen again. Yeah. You can see my screen, right? Yeah.
Yes.
So
yes, go ahead, please.
Yeah, this is our communication structure. Mainly, we have three components in this structure. The first one is VPP inode, and we are assuming that VPP inode is a mutual point in the cloud where other VPP IBOX types can connect to it, and the data of forecasted error quantifier and optimization engine are stored in this node. The second one, the second component is VPP IBOX type 1. It has Raspberry Pis and RTU, which is a remote terminal unit, and has physical communication with virtual energy storage assets. Raspberry Pi 1, you can see, hosts VS Engine API, and this one has two functionalities. As Saif mentioned that, the first one is quantifying flexibility and generating control signals for each VSS components. And Raspberry Pi 2 also have two functionality. The first one is receiving and providing live data belonging to VSS components. The second one is assigning control signals to VSS components. The third component in our communication structure is VSS, which is Virtual Energy Storage System. And this one has three components. The first one is button energy storage system. Second one is flexible load, and the third one is diesel generator. Between Raspberry Pis and VPP inodes, we develop REST API-based communication architecture. And between Raspberry Pi 2 to RTU and the virtual energy storage system components, we use Modbus TCP communication. And this structure is operated in mainly two different scenarios. In the first scenario, Saif also mentioned that if the difference between real and forecasted energy generation is below a certain threshold, this means that the forecast error quantifier assigns this error value to 0, and this means there is no error and there is no need for VSS components. And then VPP inode sends optimization engine control signals directly to the VSS components. And in the second scenario, if the deviation between real and forecasted energy generation is above a threshold, forecasted error quantifier determines this value as an error, and this error need to be compensated by the VSS components. And in this situation, VPP inode sends this error data with optimization engine control data to the VSS engine API. And then VSS engine API or VSS engine is activated and generates control signals which are trying to compensate this error value. You can see a simple decision algorithm here, which I explained in previous slides. So there is a while loop which continues for the length of or the duration of the optimization engine data or a specific time frame. And each time step, it checks at first FE value. This is determined by forecast error quantifier. Again, the value of the FE equals 0 means that the error between real and forecasted energy generation is below a certain threshold, and this means there is no error. As you can see in this situation, from the VPP inode, there is a post request method, and it calls the VSS API in Raspberry Pi 2. And optimization engine data is sent to the VSS API. Then VSS API directly assigns these control signals to the VSS components. In the second case, if the FE value is not equal to 0, which means the error between real and forecasted energy generation is above a certain threshold, VPP inode sends FE value and optimization engine data to the VSS engine API to activate the VSS engine. Then VSS engine use this data to start its own operation and generates control signals to compensate errors through VSS components. And this is our communication and control methodology for VSS components. And I think, if you want, if you have any question, I can address, or I can leave the floor to Saif again.
Yeah, many thanks, Mehmet. So back to the VSS engine algorithm. So in order to test this algorithm before being deployed on the island, we've had to create simple models that represent the VSS components. So we created a simple model of flexible load, which has a 3 state of operations: available, unavailable, and standby, and a model of a battery energy storage system, and a model of a diesel generator. The model of diesel generator was developed based on the constraints adopted by the optimization engine, which is deployed at the VPP4I node. Sorry. So we've also created simple test signals that represent the signals sent by the optimization engine from the node. So I'm for the 3 components, but I'm only showing the signal sent to the battery. So showing the signal sent by the optimization engine to the battery in the red dotted lines, and the output from the battery in the blue line, and the associated state of charge is also shown. So this is an example of the output from the forecasting error quantifier. So essentially, when this signal is positive, that means the forecasting error is essentially positive, and that basically means that the real power output from renewable generation exceeds the forecasting value. So this surplus power should be mitigated by the VSS, which is in this case operating in the charging mode. And when the signal is negative, the VSS need to be operating in the discharging mode. So the VSS algorithm operates at 1 minute time steps. It can operate at shorter time steps as well. So the VSS charging and discharging powers are again the aggregated response from the flexible load, battery, and diesel generator. And the response to the forecasting error is quantified as the output of the VSS components away from the optimization engine setting points. And hence you can see that we have DP, which represent the change in the power from each of the components, and the aggregated power by which represent the DP VSS. So we've assumed here that we have an optimization signal as a baseline powers, and again the deviation away from that is a response from the VSS. So if we take, for example, the first part of the figure where we have a positive forecasting error, we have actually the setting point for the diesel generator is a 300 kilowatt, and what you can see is a deviation from that, which is a reduction in generation. But due to a gradual reduction in generation from the diesel generator, it's taking place, and it's restricted by the ramp down constraints of the diesel generator, and therefore the response from the battery and the flexible load are compensating for the error at the early stages before reaching the steady state where each of those components have a constant value over the next couple of minutes. So again, the VSS output is aggregation in the response of the flexible load, battery, and diesel generator, and you can see that it's fully mitigating the error in renewable generation. So back to the setting points that we've assumed for each of the components, and the power output from from battery, diesel generator, and flexible load when VSS is activated is different, and the difference, as we can see, is what we assume to be the response to the error in the forecasting of renewable generation. That's all from our side. If you would like to have more information about the VSS engine, we would invite you to have a look at our conference paper published this year. Many thanks.
Thank you, Sami. Thank you, Mehmet, for your presentation. I think also we have published an ebook, VPP4 for future energy community, maybe can be a good reference also for our project. So, Ionis, is your, you can introduce Nucotech yourself and yes, your decentralization energy management. Go ahead, please.
Thank you. Let me share my screen. One moment. Can you see my screen?
Not yet. Yes. Now it's okay. Go ahead, please.
Is it okay? Okay. Thank you.
Yes.
In this presentation, we are focusing on the decentralized energy management platform that is being used in the overall solution of VPP4 Islands. The blockchain-based decentralized energy management platform has the following focus points, scopes, to enable a decentralized auctioning system for energy transactions, to record energy transactions using distributed ledger technologies, and to issue certificates for the energy production and consumption. Like a short background for the whole of it regarding blockchain technology that is being used, blockchain is a peer-to-peer decentralized network that provides transparency, security, and immutability in the data within the network by using cryptographic techniques and consensus algorithms. And on the other hand, smart contracts that are also used in this framework are self-executing contracts in the blockchain environment, which enforce trustless negotiation between two or more parties in being involved and communicating and exchanging data. So the key features of blockchain technology is means that it is trustful, it is immutable, it is transparent, it is secure, and of course it is cost effective. So let's pass now to the system and components that is being used. It is consisted of Raspberry Pi devices, Ethereum client interface, auctioning smart contracts, logging and certifying smart contracts, and the communication between the platform modules. The system architecture actually is, as we see in this diagram, it consists of 3 Raspberry Pi devices forming a private blockchain network. Each Raspberry device represents a node in the network as they are presented before, auctioning smart contracts and logging smart contracts. How the system is operating, it is being done like in the diagram that you see in the screen. And specifically after the node 1 establishes the network, 2 additional Raspberries connect to constitute as 2 additional nodes. Smart meters connect to the VPP platform. Meter readings are then recorded to the blockchain environment. Energy transactions are recorded. Energy certificates are issued, and auctions are also facilitated. The software tools that are being used for this overall thing is like the ones you see in your screen. So specifically to set up the Ethereum client in the blockchain environment, to the appropriate software modules to deploy and test the smart contracts, to interact with the Ethereum nodes, the version control, the browser, the needed browser extensions for managing blockchain wallets, etc. So regarding the auctioning smart contracts, their role are to create auction, so to define the auction duration, the initial price, the energy amount considered, the consumption start date and the consumption end date, to place the bid. The potential energy buyers are able to bid in the auctions, and to complete the auction, when the auction duration passes, the auction seller is able to end it and get his money and send the energy as it is configured. Regarding the logging and certifying smart contracts, initially they record the energy transactions from the sender, who is the sender, what is the energy amount considered, what is the source, is it renewable, generated, etc., and what is the type, are we talking about production or consumption. Then fetching the data regarding selected or all energy transactions, and then to provide the energy certificates, so the energy transactions in the blockchain also act as energy certificates. The communication to and from the private blockchain environment is established through RPC API endpoints, and the external connector establishes connection with the private blockchain environment and is able to deploy new or interact with existing smart contracts. Future developments to be considered for a further stage of developments could be to load further balancing across the nodes. Could be also regarding the energy reconciliation if the energy produced and consumed is not was initially agreed, and to set up business rules needed to define in order to apply supported by the same technologies. And regarding the scalability, because 3 nodes are not enough to ensure decentralization across the network in real auctions and in large scales. Thank you very much.
Thank you. As we still have time, I don't know if you want to introduce Newcotech. I know it's spin-off linked to blockchain 2050. It's up to you.
Yes, Newcotech is a technological company. It's an SME actually, which is based in Athens, Greece, and its main work pillar is blockchain applications and platforms, and in commercial or research works. We are actually a rather newly established company, but our technicians and our executives carry a lot of years of experience from previous collaborations with other entities and research groups regarding blockchain and regarding also IoT establishments and applications. And in this case, actually, for VPP4Islands projects, we had undertaken specific parts of the work of blockchain 2050 to implement according to our expertise.
Okay, thank you. Thank you for your presentation.
Thank you.
Now time is for questions. I don't know if any one of you have a question to be asked to our speakers. Go ahead, please. Feel free. You can put your question in the chat or just raise your hand. So. Maybe I can start. I have a question, Sami. How through the VSS, in which case the forecasting error is high, and how in which case or how VSS can reduce this gap, this error for forecasting?
Yeah, many thanks, Habib. So we know that at Gochada we have 2 wind turbines each of 900 kilowatt and one solar PV system of a PV system of 210. This is relatively not small renewable generation. The way that as a project we forecast this generation can lead to some error. We've based on the discussion with our partners, we think that 10%. So if the forecasting error exceeds 10%, then that considered to be a large error need to be mitigated by altering the output from VSS components. I think I've missed to mention that the VSS engine, as part of the solution, aims to allow those renewable generation to participate into the Turkish energy market, a day ahead and intraday market. And the role of the VSS is essentially to mitigate the error, which means that when the VSS when the whole solution participating in energy market, we guarantee that the energy delivered to the market is the energy that we've promised to do or promised to deliver. Yeah.
Yes, thank you for your answer. Maybe another question about the VSS. As one of the main objective is to decarbonize island, and I think that we have a diesel generator. So I don't know if that's possible through the VSS to replace or to fully replace the DG, the diesel generator, and in which case.
So it's again, this is a large amount of renewable generation going out from the island. It's intermittent generation. The components that we aim to install, or it's actually the installation under the way, which are only 50 kilowatt of battery and 6 kilowatt of flexible load. This, when compared to almost 2,000 kilowatt of renewable generation, is small. When we have a large amount of forecasting error, we need to use the diesel generator to mitigate some of that. When we design the VSS engine, one of the main objective is to reduce any generation from the diesel, but I don't think that we can fully replace that with the components that we have in place.
Okay, but at least we can, yes, reduce the carbon footprint impacted by the diesel generator. Okay, thank you. I don't know if anyone has any other question. Go ahead, please. Maybe I can ask you, David, for the VPP4IBOX. If, for example, the EC want to inject energy on the grid, do we need other hardware to be integrated in the VPP4IBOX, or it is already enabled, the injection of energy in the grid?
Yeah, I mean, this is enabled. I mean, needs to be supported by the electric infrastructure. What we are doing from the box is just to monitor and to provide the operator the provided production and consumption, so they can take that into consideration. Okay, but this is normally supported by the DSO infrastructure.
Okay, that's nice. It's great. Any other one? If you have any question for speakers, go ahead, please. I think there is no more questions, so I thank you. Thank you, everyone. Thank you, David. Thank you, Sami, Ahmed, Ioannis, for your presentation, for your time and contribution. And thank you all for your attending this meeting.
Okay.